Yeah, 7 long minutes until you're supposed to start.
Right. Should I plug in my computer?
Also, I want to like the
Oh, yeah.
Yeah. I'm wondering, is there a mic at the top? It's what, safer not to. I'll turn it on if there are questions.
Okay,
Yeah.
great. Are you gonna announce for it?
Oh, yeah, I
Okay.
will. I'll come back in a sec. So.
Okay.
I'll control volume.
Do you need a remote switch? Or you just gonna-
I'll probably just. Okay, wait.
I don't know.
Yeah, it's true. Not having volume control.
Okay, great. start on Berkeley time, which is 10 hours. I think that's up to me.
Yeah. I don't think yesterday we started.
We started right on the hour.
we did.
Right? Yeah, I think so. Little, but birthday, I have to work. And I'm supposed to check. Because it notifies her. You can do it remotely. Okay. Thank goodness. I thought I was gonna have to race back to Oakland and. Welcome back to work. She's been living in her bubble. Okay. Download this test before. You're on the other.
Morning.
All right, welcome to day 2 of the workshop. If you have a question during the talk, raise your hand. I will try and get the mic to you so everyone can hear you and the video can hear you. So we're going to kick it off today with a talk by Robert Huang, and he's going to tell us about learning from quantum experiments.
Yeah, thank you so much for inviting me. It's my pleasure to be here to talk about recently emerging subfield, which I term it called learning from quantum experiments. My name is Robert, and let's just get started. So as many of you know, one of the central goals of science is to learn how the physical world operates. In particular, by performing experiments, humans can receive information about the physical world and then process that information to form predictive models that allows us to make accurate prediction about how the physical world would behave under different scenarios. So in order to accelerate and automate scientific development, it is very important to understand how to design better algorithms to learn from experiments. So I think this is sort of a more broader topic. People in biology do it, chemistry do it. But here today, I'm going to talk about sort of an emerging and burgeoning field in quantum information theory that considers the task of learning from quantum experiments. So the outline of today's talk would be given as follows. In the first part, I would just talk about the basic settings and some of the example tasks that we care about. In the second part, I would talk about some of the key ideas. And at the end, I would finish with some outlook and open questions. So let's begin with the first part of the talk. So the basic setting is in this field is very simple. There's an unknown quantum object. So it could be a quantum state, it could be a quantum process, quantum dynamics, or it could be something even more crazier, such as an entire phase diagram. So for people that are not familiar with phase diagram, what that means is basically you have some parameters that you can control, and that parameter corresponds to a class of Hamiltonians, which corresponds to some physical system. And then you care about, say, the ground state of the Hamiltonian. So you have some parameters and the corresponding ground state. That's a much broader object than just a state. It's a function from parameters to the state space. And the goal is to learn that object from experiments so that it becomes approximately known. And the key question that we care about is how many experiments are needed in order to approximately learn this unknown object. So we care about the sample and query complexity. That's the two main complexity measure that we care about in this research line. And one of the goals of this line of research is to provide a foundation, a learning theoretic foundation for various applications, including quantum benchmarking, quantum machine learning, quantum sensing, machine learning for physics, noise characterization, variational quantum algorithm, etc. And so now in order to start diving into sort of what are some basic examples of this. So this is just a basic setting. It's very general and very vague. And I wanted to talk about some specific examples that people have studied extensively. The first example is what we call quantum state tomography. There's an unknown n-cubic quantum state described by a density matrix. And the goal is to learn a classical description rho hat by performing measurements on multiple copies of this state rho, such that after learning, we want this description rho hat to be approximately equal to rho, say under the trace norm. So the trace norm basically means that for any observable with a spectral norm bounded by 1, the state rho hat would have the similar property as rho. So what are some motivations for studying these questions? I think one of the main motivation is that this is one of the simplest quantum learning problems that one could think about. So by understanding this, I think it illustrates a lot of different aspects in terms of learning about quantum systems and learning from quantum experiments. And another more practical motivation for considering this is to benchmark quantum system. So experimentalists often create some kind of many-body system in their lab, and they wanted to know what is this particular system that they have created. And by performing quantum state tomography, the experimentalist can at least verify or understand what's the state that they have been creating. So there's a long list of works that look at quantum state tomography. Here are just a few references. People started by looking at Wigner function in order to do quantum state tomography. There's also methods based on compressed sensing. And then more recently, actually, that's already like 6 years ago, Ryan O'Donnell, John Wright, Jianwen Ha, and other people, they've cooked up the optimal protocol for doing quantum state tomography. It's optimal in the sense of sample complexity. So it uses the minimal number of samples, that is number of copies of the state, in order to learn about this rho hat. So however, due to the sort of a strict measure of trace norm, performing quantum state tomography has a complexity that scales exponentially in the system size. So in practice, you can only do quantum state tomography for very small system, like maybe a system less than 10 qubits. I think 7 or 8 is the maximum people have gone to. So in order to circumvent this exponential scaling, there's another very related task, which is called shadow tomography. Scott Ernst proposed sort of this task. It's very similar to the quantum state. It's very similar to quantum state tomography. The only difference is in how you measure success. So in quantum state tomography, we measure success by constructing this representation rho hat that is equal to rho, that is approximately equal to rho under trace norm. Here, we relax that condition. We don't care about trace norm, but we care about, say, a set of observables, O1 to OM, and we only want the description to be accurate for this set of observables. So this could be a very large set. M could be very, very large. However, it's not all sets, all observables, because if you care about all observables, then that would be the same as quantum state tomography. So here we usually consider this capital M to be something, say, exponential in system size or something like that. In general, the number of observables scales doubly exponential in system size. So since it's very similar to quantum state tomography, I would say this is sort of the second most basic quantum learning problem. So that's one motivation for looking into shadow tomography and understand its complexity. And another more practical one, similar to before, is to benchmark quantum systems such that you have a much better scaling in system size. I will talk briefly that the complexity scales much more favorably. And furthermore, by having an efficient methods for constructing a classical representation for any quantum state, you allow sort of a nice interplay between the quantum world and the classical world. So shadow tomography has now become sort of a basic primitive in various hybrid quantum classical algorithms. So that's another motivation for considering shadow tomography, for understanding the complexity of such a task. And starting out in actually 2018, shadow tomography of quantum state by Scott Ernsten, and then following by multiple people that try to improve upon it, such as Costin Badescu and Ryan O'Donnell's work on improved quantum data analysis, our work on predicting many properties of a quantum system from very few measurements. We have now sort of understand the complexity for the sample complexity for doing shadow tomography. In particular, under the most general setting, the complexity scales linearly in system size rather than exponentially in system size. And in certain cases, such as in the settings that we have looked at, the complexity is actually independent in the system size. So now you have this very efficient way to learn about a quantum system.
To be clear, the sample complexity is still not pinned down.
That's true. That's true. So it's not entirely clear that this is linear. I'm just saying the upper bound is linear. We don't really have a lower bound that says it has to be linear in various cases.
Right. But you know, could it be independent of system size in general? We don't
Right.
know that yet.
Right. Yes, it is dependent on M. Yeah, I should also. Yeah, I was about to say that. The dependence on M is also very mild in the sense that it's usually, say, logarithmic in M or Pauli logarithmic in M. We also haven't pinned down the complexity yet. That's the second example. And now I wanted to switch here and talk about the third example. So there's a lot of different examples that we wanted to perform learning. Another very common example is called Pauli channel tomography. Here, rather than having an unknown quantum state, you have an unknown Pauli channel. So for people that are not familiar, basically Pauli channel just means that you have some probability distribution over Pauli errors. That is tensor product of X, Y, and Z, or identity. So this is a very important task that arises in, say, error correction and fault-tolerant quantum computation, etc. So usually there's an unknown n-qubit Pauli channel P, and we wanted to learn a description for P by preparing input states evolving under this Pauli channel and measuring the output state, such that after learning, we have a description that's close to P under the diamond norm. So the motivation for this, as I briefly mentioned, is to characterize quantum noise in quantum devices. And after learning about the quantum noise, it could be very useful for performing better quantum error correction or doing error mitigation, etc. There's also a long list of works that study this problem, starting from Steve Lamia and Joe Woolman's work on efficient estimation of Pauli channels. And then there's a lot of other developments that have gone throughout the years. The complexity is a little bit more, it varies. So in general, when you just have a Pauli channel, the complexity still scales exponentially in system size. However, people often make certain assumptions about the sparsity of the error or certain locality assumption. And making that assumption often makes the complexity much better. And in many cases, it could be, say, logarithmic in N or polynomially in N. The final example I wanted to talk about is predicting ground state. It's, again, another very different example. Here, instead of having an unknown state or an unknown quantum process, we have an unknown function that maps parameters to the ground state of some Hamiltonian h of x. So you can think of it as there's an unknown phase diagram for the entire sort of physical system, entire set of physical systems. It's not just a single physical system. And we could learn this f hat by, say, preparing ground states under different parameters and then measuring the state. Such that after learning, given a new input x, we can predict what the ground state of that Hamiltonian is. So this line of work is not really actively studied in a more theoretical fashion, but it has garnered a lot of interest from a more practical side, starting from Giuseppe Carlio and Matthias Streyer's paper on solving the quantum many-body problems with artificial neural networks to this ICML paper on neural message passing for quantum chemistry. There's a lot of excitement about using machine learning or learning approaches or learning algorithm in order to speed up computation of, say, ground states or computation in quantum chemistry and quantum physics. For example, this paper by Justin Gilmer and other collaborators, I think, has about like 4,000 citations at the moment. Which is...
Yeah, just could you say whether the difficulty here or the central issue here is the unknown F or the nature of the ground state?
Yeah, I think both are hard. So even if you completely know F, this process can still be very hard, right? Like in general.
And so can you say physically what's the relevance of F? How do you think about it?
So I think it's like in a physical setup, you have some parameters you can control, and you might not really know when you control that parameter, like say you tune the lasers or you modify certain aspect of your device, how the actual physical system is generated. So in that case, it will be kind of unknown. Of course, you can assume that it's known. I think that's usually what people in Hamiltonian complexity consider the problem. But here you can also say, what if we don't know? Like we just have parameters, like the experimentalists can tune those parameters to create different materials under different circumstances. Can we understand and make prediction about the ground state? So that was
I mean, presumably this problem of predicting a phase diagram goes back earlier than 2017, right?
Yes,
more like
definitely.
1917 or something.
Yes. Yeah, these are just like more where people explicitly use machine learning algorithms for doing it. And yeah, these are just 4 examples. I think there's a lot more examples that you can just put your problem, and then because I think all problems contain some aspects of learning about an unknown object, and you can just pick your problem and then put it into this and then rigorously study using learning theoretic tools. I think there's always going to be something interesting that's going to happen. And here are just a lot more problems that people have been asking me about. Some of them are kind of crazy, like the 4th one, but there are also some more concrete. I think the first question that I'm personally very interested in is understanding what kind of quantum circuits or what kind of quantum algorithm can we actually learn, in the sense that there's some unknown quantum circuit, and then you wanted to learn it. You wanted to be able to learn it so that you can mimic that or make prediction about it, which I think is a very important question in quantum machine learning and variational quantum algorithms. There's also questions such as what aspect of an unknown quantum machine is learnable. I think Yunxiao Liu will be talking about that question quite a bit later. There's also a question about how to learn a good quantum sensor given some unknown quantum machine. How can we learn the noise in order to throw it away and then get a good sensor out of it? And then the first question, surprisingly, there's a lot of people asking me that, and I don't know how to answer it, is can a learning algorithm discover new physics? I think this is a question that many physicists want to know, but I have no idea how to solve it. And these are just a bunch of examples and sort of questions that can be studied in this subfield. And now I wanted to talk about some of the key ideas that people have developed throughout the past several years in order to tackle some of these learning problems. And the talk would be separated into 2 parts. The first part would focus on upper bounds, that is how to design good learning algorithms. And the second part would be focused on lower bounds, showing that no good algorithms exist. So I'm going to start with the first part. It's sort of a recurring theme that people have been considering in the past several years in terms of designing a good learning algorithm. Consists of these 4 components in general. On the algorithmic side, people have proposed of using randomized experiments to gather the data and then followed by a proper data processing. And on the analysis side, for analyzing the performance of the learning algorithm, it's kind of closely related to how people do learning theory. Basically, you use sort of the geometry of your unknown object you try to learn to perform some kind of geometric analysis to understand its sort of like, for example, VC dimension or flat shattering dimension is one example of that. And then utilize concentration inequalities to show that after some number of experiments, you can converge to the right thing. So these are sort of the 4 key techniques that people often use. And in order to provide a bit more context to these 4 techniques, I think it would be nice if we can dive a little bit into this task shadow tomography, which I feel like is one of the most basic quantum learning tasks. And recall the task that basically you have an unknown n-qubit state, and you wanted to learn this state by performing measurements, such that after learning, you can utilize this learned description rho hat to predict many observables. So now I would like to talk a little bit about how these 4 components come into play. So in terms of the randomized experiments, one way of performing shadow tomography is to do the following. First, you sample a random Clifford uniformly from the Clifford group, and then apply it onto your quantum state rho, so you rotate it. And then after rotation, you just measure the state in a computational basis to obtain a bit stream BI. So what this randomized experiment is doing, you can think of it as the quantum state is just a high dimensional object. And then every time you sample a random Clifford and then do measurement, it's kind of like you're looking at this high dimensional object from a different angle and getting a classical shadow or classical snapshot of the outcome. And then you just perform this very simple randomized experiment for multiple times. And that's it. So that's the randomized experiments. And now what you do during the data processing is you construct for each of the experiments, say experiment I, you construct this representation rho hat I given as follows. There's this 2 to the n plus 1, which is quite a large number, multiplied to this U dagger BI, BI UI, and then minus identity. So you can do that completely classically because UI dagger BI, that's just a stabilizer state, and you can store that very efficiently on classical computer. So yeah, that's the randomized experiment, and that's the data processing. And now through the geometry of Clifford unitary, basically the fact that it forms a unitary 3 design, you can show that the expectation value of trace of O rho hat I, basically the thing you constructed during data processing, for any observable O,
Should that subscript of I be inside the parentheses?
Yes. Thank you. Yeah, so the expectation value of that would be equal to the true property for the unknown state rho. So recall that this rho is unknown here, and then the observable O is the property you know and you wanted to predict it. And furthermore, using the 3 design property of Clifford unitary, you can show that the variance of this estimation would be less than or equal to 3 times the Frobenius norm squared of the observable O. So together with these 2 facts, which stems from the geometry of Clifford unitary, you can show that for any given observables O1 to OM, such that its Frobenius norm, say, is bounded by a constant, after performing a logarithmic number of measurements, you can predict trace of OI rho for all of these observables up to some constant accuracy.
So wait a minute, so what do you actually do? Do you average the rho I hats?
Yeah, so because you only get this first 2 moments, so you do median of mean estimation instead of just averaging.
Right, median of mean.
Yeah. It's like the standard technique that you do when you only get the second moment bounded. You don't have higher moments, so you cannot just do concentration. So yeah, so that's a sort of a very simple illustration on how these 4 components play in this. It's called classical shadow tomography. The true shadow tomography is much more complicated than this, but yeah.
And the difference is that this requires the Frobenius norm assumption.
Yes.
But it's also a simpler procedure to do experimentally.
Yes.
Okay, but wait a minute. So like what you would store in memory would be the list of all the rho I hats.
Yes.
And then when you give in some new data that you want to predict, then you do the calculation.
Yes.
And then you take the median of mean of the scalar numbers that you get out.
Yes.
Thank you.
Yes. It's a very simple procedure, but I think it nicely illustrates the 4 techniques that was used in various different contexts, such as in Pauli channel tomography and all other tasks. So yeah, so through that 4 components, you get this theorem, which states that given 2 parameters B and epsilon, the procedure that I just talked about can learn a classical representation of an unknown quantum state by performing B log M over epsilon squared measurement, such that subsequently given any observables O1 to OM with a Frobenius norm bounded by B, or for Frobenius norm squared bounded by B, the procedure can predict all of these expectation value up to epsilon error. So for example, if you have 10 to the 6 different observables you wanted to predict, all of which has a Frobenius norm bounded by 1, naively, if you just measure each of the observable one by one, you need 10 to the 6 over epsilon squared measurement. But now this theorem tells us that we only need 6 log 10 over epsilon squared measurement.
Some intuition. What kind of observables have small Frobenius norm?
Yeah, that's a great question. Actually, we also mentioned it. So it's usually small for like low rank observable. And one of the application is estimating fidelity. So suppose you wanted to create, say, a state psi, or you wanted to check which state you have created, then usually you wanted to estimate, say, the inner product between this cat bra psi and the state rho. And then that would be an example where you can simultaneously estimate multiple of these fidelity. And actually, you can estimate an exponential number of fidelities by performing a polynomial number of experiments. And this is just one theorem. When you utilize Clifford unitary to do randomized experiments, you can modify that randomized experiments. You can use some other random unitary ensemble in order to rotate your system. And by changing that ensemble, you actually can slightly change the theorem. Basically, for a different ensemble, for different randomized experiments, you get a different norm. And in particular, for Clifford unitary, you get the Frobenius norm. But if you use, say, like single qubit local unitary rotation, then you would get another norm that scales differently than Frobenius norm. So more generally, you get this theorem where you have this, what we call a shadow norm. And as long as your observable has a bounded shadow norm, you can predict it. And that norm depends on the randomized experiments that one performs. So that's sort of one of the, in my mind, one of the simplest quantum learning algorithm that one could have. And utilizing these 4 ideas by constructing the right randomized experiment, doing the corresponding data processing, and doing the right analysis, there's a lot of other applications that people have come up with throughout the past several years. Here's a long list of references. But for example, people have proposed using randomized experiments to do cross-platform verification. Basically, that just means using 2 quantum computers, you create 2 states, say rho and rho prime. You wanted to check if they are the same state, for example. So you wanted to say estimate the inner product. So Andreas Elben and Peter Zola's group have worked on it. There's a paper published at PRL. And Anurag Ganshu, Zeph Landau, and Yunqiao Liu also have worked on it in a paper title called Distributed Quantum Inner Product Estimation, where they try to understand what's the best way of doing cross-platform verification. So that's one application. There's also other applications.
If it's a rho and a rho prime, you mean the trace distance or something, or the fidelity?
Actually, yeah. So actually here, at least for the 2 papers that I mentioned, they look at the inner product.
The inner product of what, though? You mean
Yeah, it would be kind of small.
Hilbert-Schmidt inner product, or what?
Yeah, yes,
The
yes.
Hilbert-Schmidt.
The Hilbert-Schmidt.
Okay,
And then you divide it by like the purity square root.
okay.
So that's one application. There's other applications such as characterizing topological order. Like for example, not sure if people are familiar, but people have heard, but there's these, people have created topological states in the lab. For example, in Google's Sycamore computer. And in order to really characterize that, they have created a topological order state. They actually utilize randomized experiments in order to estimate certain quantities that can characterize this, such as the topological entanglement entropy. And similarly, one could also utilize these techniques to probe entanglement entropy in their systems, or diagnose quantum chaos, or learn quantum noise, etc. And there's actually much more examples, and we have written a sort of a short review randomized measurement toolbox that presented more of these examples. So after talking about sort of this theorem and some of the other applications, the question that people ask me quite a lot of times is, why are we doing randomized experiments? Why don't we carefully design a good set of experiments, and then potentially after doing some set of experiments, after getting the data, we modify how we do the next set of experiments adaptively and so on. It seems like that would be much better than doing this very simple form of randomized experiments where you just randomly sample unitary and then perform random measurement. My first answer to them is that in many cases, you can prove that doing randomized experiments is actually asymptotically optimal. You may feel that adaptively choosing experiments and designing a good set of experiments is better, but in many cases, it does not. For example, in the first paper, exponential separation between learning with and without quantum memory, in that paper, we proved that for a wide range of tasks, doing a randomized experiment is the best. For example, some form of shadow tomography under the setting of where you don't do like entangled measurement, you just do single copy measurement, and you can do it adaptively. Doing randomized experiments is actually optimal. Another more recent one, actually, I think it was just a paper yesterday on tight bounds for state tomography with incoherent measurements. They finally resolved this open question that when you wanted to do quantum state tomography, doing adaptively also doesn't help. The best thing you can do asymptotically is just to actually the same protocol as this. You just sample a random Clifford and then measure. That's the best way for doing quantum state tomography when you only allow like single copy measurements.
And that gives you like a D-cubed scale?
Yes, that gives you a D-cube scaling. And if you have an entangled measurement, such as the one that John Wright has, then you get a D-squared scale.
And remind me, for shadow tomography with incoherent measurements, do we know a lower bound that's like better than for the general case?
What do you mean the general case?
Well, I mean for if you're allowed to make incoherent measurements, then
Yes.
then our lower bound is pretty poor. It's just log of m, right? But if you're restricted to incoherent measurements,
Yes.
then do we know anything better for shadow?
Yeah, so
tomography?
actually, yeah, so that's actually what we show in this first paper. So in this exponential separation
Right.
between learning with and without quantum memory, we showed that when you wanted to do shadow tomography for a general like spectral norm, like the thing you did, and you only restrict yourself to doing single copy measurement, then you can prove that the number of experiments you need is scales linearly in n. So you cannot do better than just measure each of them in general. So that's a sort of my optimized. Yes.
Is that even with adaptivity?
Yes.
Wow.
Yes. Yes.
That's really nice.
So yeah. So the first result. So the first answer to that question was kind of, it's not a very intuitive answer, but the second two hopefully provide some more intuition. The first is that by doing randomization, it can turn bad events into low probability events. And that's actually already happening in this procedure. To see that when we're constructing this rho hat I, we have this exponentially large number multiply in front. So if you choose a very, very bad observable by looking at what you get here, then you can actually make the estimation extremely bad, exponentially bad even. But basically by sampling a random Clifford unitary, you can avoid this bad scenarios basically by turning that into a very low probability event. For that case, you turn it into an exponentially low probability event.
I'm sorry, but could you give any intuition for why you multiply by this 2 to the n, by this enormous, and then subtract I? Like,
Yeah,
what's going on there?
Yeah, the intuition is that when you implement the random Clifford, that's because it's really rotating in a very wild sense in the unitary group. So after that, when you have this UI dagger BI BI UI, it's going to be quite orthogonal to anything you wanted to predict. So like whenever you have an observable you wanted to predict, it would be quite orthogonal to it. So you have to like rescale it back by that exponential number. So it looks kind of dangerous, but actually in practice it will work. And Steve Lamia and Shenrui Chen and other people from China, they actually proved that even if there's noise in your device, like for example, there's some unknown noise, there's some noise that in your random Clifford that you're applying, using slight modification of that formula would also work. So it's actually quite robust in practice.
Would that, if you increase the number of samples you take though, you need to Can you decrease the norm correspondingly? Because somehow you're covering more of the space. You see what I mean?
But yeah, and when you take more samples, then this constraint, essentially, that's like a norm bowl constraint. So when you take more samples, so now your B becomes larger. So then yes, you can grow the norm bowl. Oh,
Because you're arguing that if I take a small number of samples in some sense, then you're going to be orthogonal.
I see.
Now, if I have a nicer covering kind of the space, then somehow you might kind of shrink the work.
I see. Yeah, but actually, I think, okay, so first of all, here you can see that there's no 2 to the n coming in the theorem statement. So it's kind of just, I would say, inside the calculation, there's this, it pops up. So I don't think this is not bad at all. It's just a little bit surprising that this is there. And regarding what you said, I think it's true, but it requires you to take an exponential number of experiments so that you actually cover it up.
Sorry, so this 2 to the n factor is independent of the rank of O?
Yeah, that's just a fixed number. You don't really care about what the observables are. You just always multiply it by 2 to the n plus 1.
Doesn't this big number, doesn't it to some numerical instabilities when you try to run it?
I see. Yeah, so one has to be a little bit careful on the numerical side in order to circumvent certain numericals. Yeah, so basically you have to like usually if you just encode it into floating points, it's limited by some number. So you have to, at least when I was implementing it, I cut it up so that I represent these factors in like it's like this big number. Like you just represent the floating point in an array and things like that. So there's ways to get it. Yeah, and then in addition to randomization turning bad scenarios into low probability events, if your information is distributed quite evenly in sort of different experiments, then by doing Monte Carlo sampling, it can quickly converge to the right thing, kind of similar to how people do Monte Carlo integration, which doesn't have a dimension dependence and so on. So that's it for the first part. And then I would like to dive into the second part, that is proving no good learning algorithms exist. So why do we want to do that? In particular, here we are going to focus on conventional experiments, and it will become clear why we wanted to do this for conventional experiments. So what I mean by conventional experiments is basically sort of an abstract model for what scientists currently do in the lab. We model the scientist abstractly as a classical agent shown by this gray robot that can receive, process, and store classical information. Basically, you can receive classical information by doing measurements, process it using classical computation, and storing them in a classical memory. And together, the classical agent can utilize these classical information to make prediction about what kind of property does this unknown quantum object has, and so on. However, as quantum technology starts to evolve, we can imagine what a future experiments could be like, where we have a quantum agent instead of a classical agent. So the quantum agent receives, processes, and stores quantum information. That is, we assume that utilizing advanced quantum technology, we can use quantum sensor to retrieve quantum information, process it using quantum computation, and storing them in quantum memory. And together, the quantum agent can utilize quantum information to make prediction about the unknown quantum object. And by proving lower bounds for conventional experiments run by classical agents, it can help us understand what are the potential quantum advantage in learning from experiments. So perhaps in the future, we can utilize a more advanced set of, say, quantum sensor, quantum computer, and quantum memory in order to, say, better detect how two massive black holes is colliding in the galaxy. So actually, people are already doing that using quantum sensors, but I think, it's very rudimentary quantum sensor. And I think there will be a lot of opportunities also of incorporating quantum memory and quantum computers into it. But in order to really understand the advantage of using quantum technology in these kind of scientific settings, I think it becomes very important to prove lower bounds for what we can do in a more conventional setting.
entangled in your model? Like parts of the experiment can be entangled in some sense? Like it can entangle like starting with I don't know, the processing and so on, or
Oh, you're asking in this setting,
yeah.
which part am I getting quantum information from, or how it's
And yeah, where,
entangled with it?
yeah, exactly. Yeah.
Yeah. So, for example, are you asking like practically or more abstractly? Abstractly, I'm actually going to talk about it right here. So yeah. So Alex was asking, it's a little bit back what I just said. So now I wanted to make it more formal, and actually we designed this mathematical framework to talk about conventional experiments and quantum enhanced experiments in various settings. Is also called an incoherent setting and a coherent setting, because that place you cannot coherently store quantum information, but in here you can. And such a framework has been considered, for example, in Bubak and Lee, in Fox 2020, our previous paper at PRL, and also Aharonov, Jordan Collar, and Xiaoliang-Qi's paper, actually it's now published at Nature Communication, on quantum algorithmic measurements. So in order to illustrate it in a better way, let's consider a simple task of learning about an unknown physical system, that is an unknown state rho. We assume that there's some physical source that can generate a single copy or a single sample of rho at a time. And the goal is to learn about this state rho. So in the conventional setting, what we can do is we can query that physical source and get a quantum state, and then perform a measurement on the quantum state in order to obtain some classical data. We can store that classical data in classical memory, and then process that classical data to select the next measurement. And then after selecting the next measurement, you perform the measurement again, obtain data, store it, process it, and repeat. So this is actually very similar to what we talked about as the adaptive kind of setting, where you can adaptively choose the experiments you do next round. And when you utilize the randomized experiments, you basically remove the part on processing. You just do a randomized experiment, get some data, store it, and then do it again. You don't actively choose what you do next.
I mean, how is this different at all from the adaptive measurement?
Yeah, it's the same. It's the same. It's the same. It's just I think more precisely in the literature, it's also called adaptive incoherent measurement,
Sure.
or adaptive single copy measurement. But here, just give it a more common name for the same thing. So now we have this classical memory that stores all the data from all the POVM measurement outcome. We can then process it and then make prediction about the physical system rho. On the other hand, for the quantum enhanced setting, this is basically sort of the settings that this is more of the entangled setting. So basically what you can do is you can use quantum sensor to obtain quantum information, store it in quantum memory, and then in the next round, you do the same. You use quantum sensor to obtain this quantum state, store it in quantum memory, and repeat. So at the end, you have this quantum memory that stores all copies of rho, which you process them using quantum computation. And then after that, you can make prediction based on the outcome. So that's sort of the more precisely how the two settings is involved. I hope that clarifies your question. So here's just a summary between the two settings. In our paper, we also call it algorithm without quantum memory and algorithm with quantum memory, because the main difference between the two cases is literally whether you have this quantum memory that allows you to entangle quantum information from past and future experiments.
I have a silly question. So can you, in the second case, can you make partial measurements to determine the next?
You mean here? Yeah, you can definitely also do that. But I think, yeah. So now, so now we can, after defining these two classes, we can then analyze all the possible protocols or algorithm that the classical and the quantum agent could do to study their corresponding learning ability. In particular, here's just one example of an advantage, of a type of quantum advantage that separates the classical agent and the quantum agent. Here, the task is as follows, kind of similar to shadow tomography. Basically, the classical or quantum agent will learn the classical model of an n-qubit state, and such that after learning, one can utilize this classical model to predict, say, the magnitude of an Pauli operator P from this set. And there's a theorem that was stated. Basically, it says that a classical agent would require at least 2 to the n experiments to predict just one adversarially chosen observable from the set, but quantum agent only requires order n experiments to predict all of the 4 to the n observables.
This is basically the separation that you talked about before for coherent versus incoherent shadow tomography, but just instantiated to the Pauli observable.
Yes, 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 yes. This is actually also from the same paper, the exponential separation between learning with and without quantum memory. The result is slightly different because for Pauli observable, say there's 4 to the n of them, so you can set m equal to 4 to the n. But now you can see that the classical agent only needs 2 to the n. That's actually tight. So it's only square root m. But I think we proved that more generally it scales m. So this is an example of an exponential separation between having a classical learning agent that only do measurement versus a quantum learning agent. And the basic idea underlying this theorem is that for a classical agent, it would be hindered by uncertainty principle. Basically, all of these Pauli operators are highly non-commutative from one another, so they're incompatible. When you get information about some of the observable, you get no information about the other, in a sense. So due to this uncertainty principle, it hinders the learning ability of the classical agent. On the other hand, a quantum agent is not hindered by this type of uncertainty principle. And furthermore, this exponential separation can already be proven even when we restrict to quantum state that have no entanglement in them, basically a classical distribution over product state. Even for that kind of states, you can have this exponential separation. And I'll be a little bit faster on talking about some of the basic.
In the previous result, the classical agent can only work with one copy of row at a time.
Yes, and it just measure it to get classical data.
Right. Does it make a difference if the classical agent can work with 2 copies at a time or something like?
Yeah, that's a great question. Actually, for this case, this exponential separation is between 2 copy and 1. So the quantum agent also just work with 2 copy.
Is there a known exponential separation where the classical agent gets like 0.1 copies and still you need exponentially many experiments with the quantum?
Yes, yes. We have a paper on that. Basically, for any k, you can construct a learning problem similar to this one, such that that requires an exponential number of experiments. But if you can store all of them in quantum memory and then do measurements, do like entangle measurements, then you only need a polynomial number of samples.
So this raises the question, can you get a sharp separation where like with K, when you can measure K copies at once, you need exponentially many, but if you can measure K plus 1 copies at once, then you can do it easily.
Yeah, that's a question that we originally seek out to tackle, but it's still open at the moment. So there's not.
I think there was a paper that sort of does something very similar very recently. It was on this.
Yeah, I think that was for like Oracle type separation, right? Rather than a state learning type problem.
So it wasn't quite exactly. It wasn't like state learning, but it had like a function. So,
yes. Yes.
Yeah, but it was sharp. It was DD plus.
Yes. Yes. I think I know the paper you're mentioning.
I think it's no, I think this one's by yeah, I think there were 2 concurrent works. One of them was with Francois and then there's the Chung, the CCL. I just remember the
Okay, all right.
Yeah, so I just wanted to briefly talk about sort of the proof strategy, especially for the lower bound. The upper bound is already shown previously. And the basic idea is to basically have a graphical representation for the memory state of the classical agent. So basically the classical agent during its learning, its memory state would change. And then we can just sort of represent it graphically. In particular, say we start from root R. After 1 experiment, the classical agent, its memory, will transition into different points. And then after 2nd experiments, it will transition into more points. In general, this could be a highly complicated graph. However, because when there's 2 knots that map to the same knots, like when this kind of subgraph happens, that means some information is being lost. So when we focus on the optimal classical learning agent, we can assume that such a subgraph doesn't exist. So the tree representation can be shown in this form. Yeah, so it could be, the graphical representation can be shown to be a tree. And depending on the underlying state, underlying physical system that you try to characterize, the transition, like the probability distribution on how the classical agent will traverse this tree will be different. And if the classical agent can distinguish the two physical settings, it must mean that the probability distribution at the bottom layer must be sufficiently different, and which means that when you have more experiments being done, the tree will be deeper, and then at the end, the bottom layer, it will be more distinct. So now building on these kind of basic ideas, one could turn this prediction task that I previously talked about into a distinguishing task. And this is sort of settings where how we do it. Basically, it will be revealed to be one Pauli, and then we set up the unknown state such that it's, for each cases, it's one of a three different scenarios. And then the prediction task basically corresponds to a distinguishing task, and we can utilize information theoretic tools to prove lower bounds for the distinguishing task, which by reduction yields a lower bound for the prediction task. That's just a very brief idea on how we establish this exponential separation. And there's actually a lot of other examples, but currently the proof technique seems to vary quite substantially for different tasks. There's many other examples where you get either exponential or polynomial separation between classical learning agent and quantum learning agent. The first example, go back to Anurag Anshu, Zev Landa, and Inchel Liu's paper, distributed quantum inner product estimation, where you wanted to estimate the inner product, the Hilbert-Schmidt inner product between two states. It has also recently been shown, actually just yesterday, like I said, for quantum state tomography. In our paper, we also show an exponential separation for classifying symmetry, quantum principal component analysis, and there's a polynomial separation for quantum state certification. For learning Pauli channel, I think there's also an exponential separation between a classical learning agent and a quantum learning agent. So yeah, so that concludes the second part of this key ideas. And the last part, I wanted to talk about some of the outlook and open questions. So throughout the years of development, I think we start to know a little bit about what we can learn efficiently, but there's still a lot of things that are very unknown at the moment, especially when we start to move a little bit closer to the application side. In particular, I think for machine learning for physics, variational quantum algorithms, and quantum machine learning, there are still a lot of learning problems that have not been studied very rigorously yet. So I believe that by building connection or trying to formalize a lot of these problems that arises practically could be a very sort of fruitful direction to consider. And finally, I wanted to talk about a few open questions which are much more concrete. The first question is, can we perform shadow tomography on broader classes of observables computationally efficiently? So at the moment, we know how to do shadow tomography for any observable with bounded spectral norm, but that's only sample efficiently rather than computationally efficiently. And if we include the constraint of being computationally efficient, we only know how to do it for, say, low weight observables or Pauli observables. I think it's become very important to understand if it's possible to do shadow tomography efficiently on broader classes. And the second question, which I've also mentioned a little bit before, is what classes of quantum dynamics or quantum circuits are actually efficiently learnable? There's many natural classes that people have looked at before, but either they're not efficiently learnable quantumly, for example, even just AC0, that's not efficiently learnable quantumly, or they are efficiently learnable classically. For example, if you have a local Hamiltonian dynamics and you wanted to learn that dynamics, you can just do some very simple experiments and you can learn it classically. So I think it's very important to understand if there's something in between. I believe there are, but it's a little bit hard to find. And we probably need more tools to understand learning behavior in a quantum setting better in order to answer this question. And finally, that's the question more closely related to quantum benchmarking. That is, can we efficiently learn if there are non-local quantum noise in an unknown quantum machine? Basically, as people know, fault-tolerant quantum computers require noise to be local. So if there's non-local quantum noise, we're kind of doomed. So can we experimentally test this by designing a good learning algorithm? At the moment, I don't think we have a good approach for learning that. So yeah, so that's it for my talk. Thank you so much for listening.
Thanks for the lovely talk. So I want to just talk about the first point a little bit more. So the procedures you talked about, like the local Pauli or the random Clifford, those look like they're efficiently implementable, right? Or
Yes.
Okay, good. So what are you talking about here when you say, I mean, could that seem to have nothing to do with the observable in question, right? There's just a norm bound on the observable. So what do you mean by beyond?
Oh yeah. But I mean, in a sense, this norm bound defines the class of observable.
I see what you mean. Okay. So I mean, but normally if you think about things like local in the sense of, many body physics local,
Yes.
that should be fine, right? I mean,
Yes.
So what kind of observables are you aiming for here?
Yeah.
Like,
So
at least
I
from
would
a
say this is
physicist point
more
of view.
theoretically driven. Practically, I think many people kind of just care about low weight observables where you only act on few body in a sense. But say, for example, I mean, okay, and then string operator, that's kind of a Pauli observable. But there could be some more complicated string operator. Maybe you wanted to learn them. So that could be another examples of such.
So, but you mentioned like the fidelity, for example, which is you can do because
so fidelity depends. So
I guess pure state fidelity.
Yeah. So for example, if that state is how to say, I think in general, if you just wanted to, okay, so that protocol that I mentioned before, that theorem, that's also sample complexity. I just talk about the number of experiments and measurements you need rather than the computational one. And for certain classes of states, you can indeed do it computationally efficiently. But I think at the moment, it's not clear. Even for just these observables with bounded Frobenius norm, can you do it computationally efficiently always?
Okay, but so then as far as like many body physicists are concerned, is this like tomography thing practically over? Or is there like,
sorry,
is like tomography basically efficiently solved now as far as like a many body physicist would be concerned? Because if you only care about right. I mean, is this the end of the line somehow? Or I mean,
I think for low weight observables, the improvement will probably, for low weight observables,
okay.
I think it's
Okay,
pretty clear that we can do it efficiently. And I think we're kind of quite close to what we can do optimally.
Very nice. Yeah.
Yeah, but when I talk to some physicists, they also mention these string operators, and some of them are quite complicated. They're not just Pauli observables, and they also said that they wanted to measure them and things like that. So I think that's another sort of direction.
Could you provide some intuitions on why doing it adaptively doesn't help? Is it possible that we just didn't think hard enough to find a good adaptive algorithm?
Yeah, so basically the lower bounds that I mentioned, that was proven, basically says there's no, we have already,
I'm
it's not
just
possible
curious
to,
about the intuition.
Yeah, I think the intuition is that a lot of these learning, okay, so I think intuitively adaptive only helps when you have a good enough intuition about what the things you wanted to measure are, and then you wanted to just kind of like pinpoint it. But a lot of the problems here is that you start out with having no information, like you don't know what that unknown object is. So when you don't know what that is, you just have to do something randomly. And then basically what happens is that when you start doing things randomly, at a certain point, you start seeing that, oh, I start to know about what this unknown thing is. But at that point, you also finish learning.
So is it possible that I first do, say, half of the measurements that I want to do, and then I already have some idea of what it is, then I can do it in a more efficient way?
I see. Yeah, I think it's possible to still get constant speed up. So here, this is more asymptotic. It's just saying that it's asymptotically optimal. So it's possible that you can first do like half of your experiments, you do some things, and then the other half, you can pinpoint it better. But that will only give you a constant speed up. And And in a lot of the cases that I've talked about, like in shadow tomography, like in quantum state tomography and other tasks, what happens really is that after you already get enough information that you can start doing better, you also already know everything in a sense. So your learning terminates.
Okay, interesting.
No, maybe it would help to just say that the coherent measurement shadow tomography procedures rely on gentle measurement, right? To like not damage the state by much and keep repeating over and over for each of the observables. And gentle measurement requires amplification, right? And amplification, that's the reason why you need this coherent measurement. So like, it would be, to me, it would be very surprising if there were a way to avoid that.
Thanks for a great talk, Robert. I have a couple more questions, I guess, along the lines of like, to what extent can we, is this like final or is this like more room for improvement? One example that I thought of was this epsilon square dependence that you have. I think you prove in some cases that it's like informationally, theoretically optimal or something, but there are definitely examples where people have improved it to epsilon.
Yes.
Which I think can be actually quite important because in a physical experiment, you often hear about like, 10 to the minus 3, 10 to the minus 4 epsilons. And, there's a huge difference between, that versus squared, like, number of measurements. That is one thing. Another thing I thought of is, I think you said that these protocols, non-adaptive protocols are asymptotically optimal. Is that kind of, for the worst case in some sense?
That's for worst.
So in
So
reality, when you have like fixed set of observables that you care about,
Mm.
maybe there's some room for improvement there, or what's your thoughts on that?
Yeah, so regarding the first question, the first comment about the epsilon scaling, I think it's true. In some of the experiments that I run, it does seems like even doing randomized experiments, you can sometimes improve it into epsilon scaling in certain regime. And then we don't understand when that happens and how does that happens yet. So I think there's definitely more to be done in terms of understanding if one could improve from 1 over epsilon squared to 1 over epsilon, at least in certain regime. I think I agree on that front. So yeah, I should take back on what I said about things being final. I think there's still a lot to be explored. And then regarding the second question, yes, when we say that these randomized measurements are asymptotically optimal, it's in a minimax sense. It's basically saying that there exists, like in this problem class, there exists certain problem instances such that doing randomized experiments is optimal. But it's not to say that you can find some restriction of it, such that doing things adaptively or doing things that are different from this very simple protocol is optimal. And I think one example of it that I know of is, I think there's a paper by Daniel Stelfranca and other people where they consider the state to be in a certain class. For example, it's a Gibbs state of some Hamiltonian. And in that case, I think what they could show is that by doing these randomized experiments, there's a novel way of doing measurements, of doing data processing, such that you can get a substantial improvement asymptotically over what we prove. Because all these proof about asymptotic optimality, we cook up some contrived states and then show that randomized experiments is optimal for those contrived states. But those contrived states like part of the problem. But you can restrict your problem a little bit and then the complexity could change. So yes.